The art of dyeing textiles has a long history, as natural dyes have been used since prehistoric times. With the development of synthetic dyes in the 19th century, the focus shifted from natural to synthetic dyes due to their superior properties. Recently, however, interest in natural dyes has increased again due to environmental and health concerns. The art of textile dyeing is an activity as old as mankind, as colored textiles have been found in archaeological excavations in the oldest civilizations. However, it should be emphasized that heterocyclic dyes have also been in use since prehistoric times. At that time, only natural dyes obtained from natural resources of plant, animal, mineral, and microbial origin were used. Many of them were, in fact, natural heterocyclic dyes, such as indigo, obtained from the leaves of Indigofera tinctoriale, and Tyrian purple, obtained from the shells of mollusks of the Muricidae family, which were used to dye textiles in blue and purple, respectively. Since the second half of the 19th century, more precisely since the invention of synthetic dyes, the use of natural dyes has been almost completely replaced by synthetic dyes due to their ease of use and better fastness properties. Although there has been a return to the use of natural dyes in recent decades, not only because they are environmentally friendly, but also because many artificial textile dyes are hazardous to human health. Nevertheless, the search for synthetic dyes is still very active, as the requirements of customers around the world are changing rapidly. Azo dyes are characterized by the functional group N-double-bond-N, which connects two symmetrical or asymmetrical substituents, of which at least one, but usually both, are aromatic. They are usually synthesized in a two-step reaction as follows. Synthesis of an aromatic diazonium ion from an aniline derivative, diazotization, and coupling of the diazonium salt with an aromatic compound, or by the reduction of nitro aromatic compounds in an alkaline medium, and oxidation of aromatic amine with various oxidizing agents such as lead tetraacetate, permanganate, and haloxy acid. If both substituents are aromatic, the dyes are referred to as carbocyclic, whereas if they contain one or more heterocyclic substituents, the dyes are referred to as heterocyclic azo dyes. All azo compounds are classified by Griffiths as donor-acceptor chromogens, DPIA, and studies have shown that replacing the benzene ring of the acceptor with a less aromatic heterocycle in these chromogens leads to a significant bathochromic shift, red shift, in the visible absorption band, which results in greater color brilliance and higher color intensity, especially in synthetic materials. Due to the structure of azo compounds, they exhibit photochromic properties. Photochromism is a phenomenon that occurs when two molecules A and B are in chemical equilibrium with each other and can be easily distinguished due to their different absorption spectra. Normally, the more stable isomer A can transform into the less stable, higher energy isomer B when excited by light. However, the B isomer can spontaneously transform into the former through a thermal or photochemical reaction. It follows that there are the following two types of photochromic systems: type T, meaning thermally reversible photochromes, and type P, which are photochemically reversible photochromes. In the case of azo compounds, these two isomers are E and Z isomers. The case of the isomerization of azobenzene has been extensively studied and analyzed. In this case, the photochromic system is of the T type, and the azobenzene in the E configuration is more stable than in the Z form. The two isomers differ not only in their structure and properties, but they also exhibit different absorption spectra in the UV spectrum. The different spectral position of the bands indicates that not only is the wavelength of light required to induce the reaction different for the two isomers, but they also have different colors. Changes in the absorption spectra between the two forms are generally not very pronounced due to a small difference in electron delocalization between the two isomers, and the color change is invisible to the naked eye. In contrast, the photochromic reaction induces a very significant change in the free volume, density, viscosity, electrical conductivity, stiffness, and porosity of the molecule. As early as 1990, it was reported that heterocyclic azo dyes can combine the brightness and high-fastness properties of anthraquinone dyes with the strength and economy of azo dyes. It is therefore not surprising that numerous attempts have since been made to synthesize ever more efficient heterocyclic azo dyes. The field of heterocyclic azo dyes continues to be dynamic, driven by the need for brighter, more durable, and environmentally friendly dyes. The synthesis and application of heterocyclic azo dyes, especially in textiles, offer significant advantages in terms of color brilliance, fastness, and versatility. The development of novel dyes, including those with antimicrobial properties, is evidence of the constant innovation in this field. However, the impact of azo dyes on the environment, particularly in terms of wastewater pollution, remains a critical issue. Innovative and sustainable methods, such as enzyme-based biocatalysis and biosorption using renewable materials, are promising approaches to mitigate these effects. Future research should continue to focus on improving the environmental footprint of dye synthesis and application to ensure that advances in dye technology serve both industry needs and environmental sustainability.